Hello everyone. So today we are going to start with week 5, that is graph and algorithm design. So in this one we are going to discuss what is a graph, what are the different shortest path algorithms, network flow problems, minimum spanning tree, greedy algorithms, dynamic programming, randomized algorithms, and summary. It may look a lot, but we in this week will just go for their introduction, that what are these. I have provided you additional videos, the link for additional videos if you want to check them in detail, but otherwise we are going to cover them in detail in the algorithms too, right? So let's start with what is a graph. A graph is a collection of vertices and edges. Like for example, in you see a map where number of cities are connected by roads or bridges, or your social media, like on computer networks, like the different computers are connected with each other using LAN or WAN or something like that, right? So all these are the graphs. A graph basically consists of vertices, which are also called as nodes or objects, and edges, which connects them. Make sure a graph may exist without edges, but it may not exist. It cannot exist without vertices. So there has to be vertices, at least one vertex. But edge set may be null. It may be that if it is possible that a graph does not have any edges, right? So do we read them? Because they are used heavily in real world as well as in computer science. We can model different networks, dependencies, state machines, everything. Everywhere you will see there are number of graphs. We generally have two types of graphs. One, we categorize them by direction, like is it directed graph or undirected graph, and one is by the whether it has some capacities or cost associated with each weight, each edge. So these are called as weighted or unweighted. For example, if you see in this graph, 1, 2, 3, 4, 5, these are the vertices or also called as nodes. Whereas these lines which connects them, these are called as edges, right? Since there is no direction defined on edges, like I can go from 1 to 2 and 2 to 1 as well. So this is called as undirected graph. On the other hand, if you see in this graph, we have one A, B, C, D, E. These are my vertices. We can also call them nodes, or we have edges, but each edge has a direction associated with it. Like I can go from C to A, but I cannot go from A to C. In the same way, we can go from B to A, but we cannot go from A to B. When directions are given like this, we call that graph as a directed graph. Now, so again, this is an example of undirected graph, whereas this is an example of directed graph. Now, you see some numbers over the edges. The reason is these are the weighted graphs, whereas there is no number associated on these edges, so these are unweighted graph, right? Okay, so these are the weighted graph. Now, what do we mean by weighted graph? That each edge has an associated weight on that. The weight may be the cost or anything. So each edge has an associated weight. Like for example, how much data can flow in one direction on a edge, or what is the capacity of cars on a road in one direction. So that is the weighted, that, right? So these are the weights assigned, like 2 to 5, 5 to 4, and so on. But this is again an undirected weighted graph, and this is a directed weighted graph because Directions are given over here. Now, let me tell you one more thing here over here. If you see a cycle in a graph, cycle in a graph means the point from which we start, we traverse back to the same point. The point from which we start, we traverse back to the same point by following a specific path. Like if you see here, from C to B, C to E, E to D, and D to C, it is a cycle that we can go in a cycle here. But on the other hand, B to C, B to D, but we cannot, like we can go to B to D, but not from D to C. We can go from B to D, D to C, but not from C to B. So it is not a cycle. Whenever a graph consists of a cycle, it is called a cyclic graph. And since it is directed, right? So it is a cyclic graph with directed graph. Whereas if a directed graph does not contain any cycle, we call it as a directed acyclic graph, DAG. We call it as if a directed graph does not contain any cycle. We call that as directed acyclic graph. If a graph contains cycles, we call it as a cyclic graph. Why I'm telling you about cycles, we'll discuss them later. Now, so as we said, why we are studying graph? Because graphs has lots of applications in real life, whether it's a social network like Facebook, Instagram and all, or navigation and mapping system which you use in your GPS, World Wide Web, computer networks, resource allocation and deadlock prevention, recommendation system, one of the heavily used, bioinformatics, project management, circuit design, machine learning, AI. There are countless applications of graphs. Then we discuss about what are the shortest path algorithms. If we are having a, for example, this one, we are having some cities. This is an undirected graph, right? Because no direction is given over here. And the weight, it is a weighted graph because cost of travel from one city to another city is given over here. Now, if I'll say I want to go from New Orleans to the Nashville, which path will be best? Which will have the minimum cost? So if I go by this way, that New Orleans to Memphis, Memphis to Nashville, it will be 3 plus 15, the cost will be 18. If I go New Orleans to Mobile, Mobile to Atlanta, Atlanta to Nashville, so it will be 3 plus 2 plus 2, 7. So this cost will be 7. If I go from New Orleans to Mobile, Mobile to Savannah, Savannah to Atlanta, Atlanta to Nashville, the cost will be 3 plus 6 plus 1 plus 2, which is 12. I can go from New Orleans to Memphis, Memphis to Nashville, or I can go from this way also. So there are lots of paths possible, but which one is with the least cost? So the path with the least cost is New Orleans, yes. So the path with the least cost is New Orleans to Mobile, Mobile to Atlanta, Atlanta to Nashville, which gives me a cost of $7. So this is a kind of shortest path algorithm where we are determining the shortest weight or shortest path. This graph is a small enough, we can determine it easily. But if we are having big algorithm, like you are having a whole state, roads, number of roads and everything, then it is very difficult to find out like this. So there we use the shortest path algorithms. So the shortest path algorithm is the problem is what it addresses, that find the path between two nodes with the minimum total cost, which is the weight. The key algorithms which we use to find out the shortest path algorithms are Digester algorithm and Bellman-Ford algorithm. Digester algorithm is based on the greedy approach and it is a single source shortest path. right? Which means that from a single source, it will find the shortest path to all other nodes. And it works with the non-negative age weights. On the other hand, Bellman-Ford algorithm uses the dynamic programming. What is the mean of greedy algorithm approach and dynamic programming? We will just discuss about it. It can handle negative weights as well, and it can detect negative cycles, but it is slower than Digestra. Again, we are having number of applications of shortest path algorithms like GPS navigation, network routing protocols, social networks, and all. Then another problem comes is network flow problem. Network flow problem is we try to find out the flow of a material. Now this material may be anything, it may be data, water, traffic, anything through a network with capacities. Like for example, I want to find out what is this is the source. S always denote the source and T denotes the sink. So what is the maximum flow of data, water, traffic can be in this graph from source to sink? Here we are having two numbers on each of the edge. First number shows the current flow, whereas second number shows the capacity. Like from S to A, the capacity of flow is 7, but 6 is currently used. So it cannot be never greater than the capacity. First number cannot be greater than ever to the second number. It may be equal to like this one. The 5 is the capacity from A to B and we are using the 5 units, right? So it is the model the flow of a material through a network with capacities we use to find out the maximum amount of flow from a source to a sink, which is equal to the capacity of a minimum cut separating them. So this is a theorem which is used to find out the maximum flow, and the algorithm which uses it is Ford-Fulkerson algorithm. So we find number of path in this one and we create a residual graph. We will discuss it later on in the algorithm too, when we will cover this in detail. Applications of this include bipartite matching, airline scheduling, image segmentation, data mining, and lots of others. Right. Then the next comes out is minimum spanning tree. In short, we call it as MST. So if we want to convert a graph or we want to connect all the vertices of a graph with minimum total edge and make sure since it is a tree so it cannot have any cycles in it, right? For example, this is a graph. Let me find. Yeah. This is a graph from 1 to 2, the cost is 2. From 2 to 3, the cost is 3. From 3 to 1, the cost is 10. Now we want to create a tree from this graph such that the overall cost is minimum and each vertex is connected like the vertices are connected with each other but does not form any cycle. So the MST for this will be this one like 1 to 2, 2 to 3. So the overall cost is 2 plus 3, 5. And if you see in the overall cost in this graph, it is 10 plus 3 plus 2, which is 15. So this is the minimum spanning tree. Again, this is the short example, so we can find it out like this. But if we are having the big graphs, so we need to use some of the algorithms again. We use Kruskal's algorithm and Prim's algorithm. So Kruskal algorithm is again based on a greedy approach which sort all the edges at the smallest edge that does not form a cycle using a union data point structure. And Prim's algorithm again grows the tree from a starting node, always adding the cheapest edge connected to the current tree. We will cover them in detail again in algorithms too. So applications are like designing the least cost network layouts in the electrical grid or telecom or cluster analysis. There are lots of applications. Then greedy algorithm. We discussed earlier that my Prim's algorithm, Driscoll's algorithm, Digester algorithm, all these are based on greedy algorithm. Now, what are the greedy algorithms? Greedy algorithms is a category of algorithm that try to find out the solution of a problem in a shortest possible time. So it picks the path that seems optimal at that current moment. Like greedy algorithm is, it does not check for the overall optimization. That what would be the overall optimization? It just find out the optimization in the current scenario, right? So greedy algorithms are quite a straightforward algorithm and it is very easy to implement and easy to understand, but they cannot provide you always optimal solutions. And greedy algorithms runs only once, so they do not check the correctness of the result produced. They may be optimal, they may not be optimal. So the process which we follow is make the locally optimal choice at each step. Hopping it leads to the global optimal, and it is never worse than the optimal solution. The pros are it is simple, intuitive, and usually very efficient, but it does not always yield the optimal solution for all the problems. Examples of greedy algorithm which uses are Huffman coding, which we use in data compression or interval scheduling. There are lots of other problems which uses the greedy algorithm. Then another one is dynamic programming. Dynamic programming is one of the very important concept in data structures and algorithms. Dynamic programming, it's based on the concept that break your problem into the overlapping subproblems and solve each subproblem only once. Store your result in which we call it as memoization or tabulation. Like for example, first of all, let's see the example that what we mean by the dynamic programming or memoization and tabulation. All of us have done the example of Fibonacci in the recursion, right? Now, if I need to calculate the, as we know that Fibonacci n is n is equal to Fibonacci of n minus 1 plus Fibonacci of n minus 2, right? Okay, now, so if I have to calculate the Fibonacci number 5, the two recursive calls will be Fibonacci 4 and Fibonacci 3. Then for Fibonacci 4, again two recursive calls will be Fibonacci 3 and Fibonacci 2. For Fibonacci 3 will be again two recursive calls, Fibonacci 2, Fibonacci 1. And same way there will be these much of recursive call. If we see over here, for Fibonacci 3, there are two recursive calls. For the same number, we are performing the same operations two times. For Fibonacci 2, for the same number, we are performing the same operations three times. That means we are doing the repetition of operations. The operation which we have done earlier, we are repeating them. In the same way, Fibonacci 1, 1, 2, 3, 4, 5. The same is repeated 5 times and Fibonacci 0, 3 times. So you can see here, we are doing the same operation number of times. What is the other way? Or by using the dynamic programming or by using the memoization. If we are calculating the Fibonacci for a number, store that in an array so that if we need that again, retrieve the value from the array instead of calculating it again. For example, for Fibonacci 3, store the value of Fibonacci 3 in an array so that if I call the Fibonacci 3 again and if I see it is already evaluated, take the value of Fibonacci 3 from the array instead of calculating it again. So all of these operations, all of these steps will be saved. You do not need to perform the same operation again and again. So it saves a lot of computation actually, and it is really a very efficient method. So again, what is the strategy behind dynamic programming? Break a problem down into overlapping subproblem and solve each subproblem only once and store the result, which is called as memoization and tabulation. So an optimal solution is to the main problem contains optimal solutions to its subproblems, right? Pros, the benefits are it avoids recomputation and efficiently solves complex problems. But the problems are can be high in memory uses because we require additional memory to store the intermediate values, and it can be the less intuitive to design because you will need to think that how you can divide the problem into subproblems. Like Bellman-Ford algorithm is a dynamic programming algorithm. Other examples like Fibonacci, knapsack problem, again we are going to do an algorithm too, longest common subsequences and all. These all are the examples of dynamic programming. Then, randomized algorithms. If all of you remember that in quicksort, we have done quicksort, that in quicksort we choose a pivot element. The pivot element can be the first element, it can be the last element, it can be the median element, or it can be any of the random element, right? So randomized algorithms basically works on a random key. They always gives the correct result or correct answer, but runtime is random. Because if you're choosing the pivot element as a last element or you are choosing the pivot element as a first element or a middle element, the runtime will vary. If we are using this Las Vegas method. If Monte Carlo simulation, if we are using Monte Carlo, runtime is fixed, but there is a small probability of incorrect answer, right? So how do we do it? We uses a randomness as a key part of the logic to achieve the good performance. It is generally simpler and faster than deterministic counterparts, but uncertainty, it has the uncertainty in the output or runtime because my key is random. Again, the example includes like quicksort, load balancing, cryptography, large scale simulations. There are plenty of applications. Like this one, we are having some inputs, we are having algorithm is executed to create the output, but this algorithm is based on some random numbers. So or it may give you result every time based on that random number. So if we summarize all of these, shortest path algorithm paradigm, we use the greedy approach or the dynamic programming. It is used to find the optimal routes. Then and next one was the network flow, which we use for iterative improvement. It is used for finding out the modeling constraint flow. Then minimum spanning tree, which uses a greedy approach, in which we connect the points to find out the minimum cost. Then greedy algorithms, are based on the local choice, not the global choice, which are based on the local choice, local minimum value it finds out. It is simple and it provides you simple and efficient solutions. On the other hand, dynamic programming, which works on the bottom-up concept. We divide the problems into sub-problems and overlapping problems, and then we use the memoization or tabulation to solve them. So it can solve complex problems with sub-problems. And then the randomized algorithm, which is based on the probability, random numbers. It has speed, simplicity, and uh, estimation, right? So these are the topics for this week. The detailed link or the detailed video links I have provided in the resources. So if you want to learn them in detail, just go through those videos. And if you have any problem or any issues, just let me know. Till then, bye and take care.